Yeah, you're gonna have to spell it because these fruitcake channels.
Ginger, as
Ginger,
in the
Ginger, and I
sugar
believe
bush.
Okay.
the last name is Sugar Bush.
Is that a
Yes,
Spelled
sir.
space
just like it
sugar
Yes,
bush?
sounds,
chocolate.
and then 905.
Is that a space sugar
Yeah.
bush?
Yeah.
No, one word. Is it? Is it? I
Oh,
thought it was one word.
jeez.
Okay, no worries.
Oh no.
Doesn't matter. You'll find
Ginger
it
and
anyway,
then
John.
Sugar Bush is one word. Yeah.
Ginger sugar bush
905.
905.
Yeah,
Ginger
yeah,
sugar bush
it's worth finding it because
905.
I thought my name
and then you'll
was
see it will say
Fluffy.
Jeranism and DITRH. Found it, John.
Jeranism DIR 3 days ago, and you said 9:30.
Yes, sir. Yeah, 9:30.
9:30. Hold on a second.
There has to be some sort of force required behind it. Now, I think that that's a great statement, and like I told Bob yesterday, I'm going to have to look into this a little more. So the first thing I did was tune in to the Nathan Oakley live Flat Earth Debates channel this morning to hear him talk about it, and they did. They discussed it for about 45 minutes or an hour, and they completely missed the point simply because they didn't address the acceleration issue. They just kept going back and saying, yeah, but if you're in the water, something might rise in the water and because of the medium it's in. And I understand all that. That's a great argument. It's been my argument the whole time, but they missed the issue. So if anybody from Nathan Oakley's show is listening and they're going to be on tomorrow, please address the acceleration issue. I think it's quite important, and I want to hear the answer. But Dave.
Good enough. I got it. Who was playing that?
Me. I'm recording this. So I'm now recording.
Playing.
Just FYI, hold on. FYI, I'm now recording this, so there'll be an address.
Yeah, well, I started playing it, and I heard an echo. I said, what the hell? And it was you playing it. Lovely. Yeah, so what's your answer to him, Nathan?
What acceleration? Generally speaking, as I look around and observe the world around me, I see everything in equilibrium. Now, occasionally, there is an exception to that rule. So, for example, a leaf falling from a tree or rising up if it's at the bottom of the ocean. But without, other than those exceptions... Sorry, my kid's making a right racket.
That's okay.
So other than those exceptions, generally speaking, what we observe is the world in equilibrium. And if there is a direction to be attributed, it's caused by the medium. So the acceleration is the item, in this case leaf, being forced out of equilibrium and then finding equilibrium once more. Well, there was a huge amount of energy put into the leaf for it to grow up into the air, and it remained in equilibrium the entire time until a gust of wind broke the stem, and then it reached equilibrium when it met the ground, or in the case of underwater, when it went and reached the surface of the water. But ultimately speaking, all it's doing is seeking an equilibrium, and unless put out of equilibrium, there's not going to be any acceleration. So my question back would be, what acceleration? As I look out in the world, I don't see accelerating bricks or eggs floating up through puddles or things accelerating in any way, shape or form. I tend to observe equilibrium. So this notion that things have a tendency towards the ground with acceleration is nonsense. I observe equilibrium as a general rule. That would be my answer.
Yeah, and here's my answer. You can't take acceleration in a vacuum, no pun intended. What you're alluding to is Newton's equation, correct? Force equals mass times acceleration. So you just can't pull acceleration out. You have to take the whole equation. Now, any mathematician is going to tell you that each variable in every equation must be defined rigorously. So your first mission, Jeran, is to define mass. That's it. I want you to define mass. And when you can't do it, that answers your question. Thanks.
Can't we do it in this presentation? So what you'll find is there's a couple of different definitions. One will be for inertia. That's how they'll describe mass. The other will be for mole. So those are the definitions, unless you know of a third, John. Correct me if I'm wrong there.
No, they're going to say the amount of matter in a substance, or they're going to give the definition of inertia. Well, You can't have those definitions. You can't have two definitions for the same word. Not in science, you can't. You can when you're playing the colloquial game, right? But if you try to do that, it's called an equivocation fallacy. And you need to look up what that means. Whoever's doing this.
Okay.
So, Nathan,
Well-
you're correct. He's not going to be able to define mass, so the equation falls apart.
Okay.
Can I ask
I mean,
a question? I got a phone call and I couldn't hear everything, but can I ask a question about this?
Yeah, go ahead, Paul.
So they said the force is the issue, or they keep bringing the force thing. So if I miss my words up, don't jump on me too hard. But forces would only be in play if something's in motion. But once it's at rest, you can't equate the force. Am I understanding that right? So force would not even be even in play. So it has to be in motion to even apply force. Do you understand what I'm questioning or what I'm asking? No, yes, maybe.
No, and I have
makes
to go
sense
for a
to me.
second. I'll be back.
Do you what now? I'm sorry. I didn't
No,
hear you, John. Say it again.
I didn't hear you, Paul.
He said he's nipping off
Oh,
for
you
a
didn't
second.
hear-
I don't know if anyone else on the
Okay.
panel.
Okay,
I'm
is that
leaving these
better?
gaps because the question was addressed kind of to the show as opposed to just to me. So
Can you hear me better now? Is that better?
we heard you. I'm hoping someone else on the panel will address what you've said, because the question was phrased to the panel, right? To the show, i.e. the regulars, you guys.
Well, Paul.
Yeah, anybody.
Well, I'll answer. Yeah, like what you were saying, Paul, does make sense. Like you were saying that once a force is applied, that's where the acceleration would be assumed. But if the object is just at rest, then there's no acceleration or force being exerted on the object. It's just in equilibrium. So it would only be once that object is disturbed, that's what would cause the force or the acceleration. So I think that's what they're missing. They're trying to figure out like, well, what causes the acceleration? It's it being taken out of it being taken out of its equilibrium that's causing that acceleration or whatever. Like that's what I'm thinking that it is. And but they're still trying to call it something, and it's like it doesn't have to be something. It just has to be that's what's happening. It's being taken out of its state of inert, like it's being taken out of its,
But here's the thing. I think they agree that, relative that things move because of the relative density of the medium they're in. I think it's just after something starts moving, then if it starts accelerating, they assert that they apply that to a force. Like if I go to the top of a building and I drop a brick, the brick will probably be moving faster before it hits the ground than it is after I release it out of my hand, right? So they're saying that acceleration is due to some force, and to me, there's no force. I mean, I drop the brick, it's not going to be held up by the air because it's too dense. And to me, it's just whatever it's made out of and combined with its momentum is just going to give it acceleration. I don't see an outside force acting on it. That's just me.
Let me look.
Yes, I agree with that. That's my point too.
Here's something I was thinking about yesterday. I was talking to Anthony a little bit about it yesterday, but just thinking about it from the leaf falling analogy. Now, we know when a plant grows, we've talked about it already, the plant itself is actually, using energy to grow. It's, producing leaves and the branch, the trunk, the whole 9 yards. There's a lot of energy being utilized to, in a sense, to cause that tree to grow. Well, when the leaf disconnects or is loosened from the branch, some of that energy that's been pushed into that to push it, so to speak, out of equilibrium, it's being released back down to put the leaf back in equilibrium. So to me, every time I think of you're pushing it out of equilibrium, you're in a sense putting kinetic energy into that to force that out of that. So when you let go, it wants to go back to, like Nathan says, equilibrium. So there's where the force is. It's like the energy being released is the force, so to speak. Is my thinking wrong on this? But that's how I'm starting to understand it.
But if all right, so
No,
I mean,
it's not.
correct me if
Wait,
I'm wrong
actually,
here, right? If so, if force is mass times acceleration, right? So mass, let's just say mass is whatever the thing is made out of, and obviously once I let go of it, let's say the brick on the building, I let go of it, it's going to start accelerating. Isn't that like the force itself just coming from whatever it's made out of, plus me releasing it into the medium where it's not going to be held? It just kind of creates its own force. Now, obviously, I could be wrong, but I just don't see an
Well,
outside force affecting it.
you keep on saying, see, this is the problem. You keep on saying, and it's not only your problem, we all have this problem, Vanilla. I'm not trying to, isolate you, is that we keep on parroting force, force this, force that. What are we in friggin' Star Wars? Right? There is no force. It's undefined. And his laws are the law that those three laws are friggin' a train wreck. Let me just say this. Listen to this closely. From the chair of physics at Yale, the laws of physics are always quantum mechanical laws. You don't have separate laws for big and small things. I'm not done yet. Richard Feynman, king physicist, and I quote, the discovery of quantum mechanics first, and then in the behavior of light, and then in the behavior of matter, finally culminating in 1926 with a full equation of quantum mechanics, which told us that, here's the punchline, the laws of motion of Newton were not right. And it had to be modified with other laws, which are quantum laws of motion. The prosecution rests.